Venus will kill you in seconds. The pressure will crush your skull. The heat will vaporize your lungs. The acid rain will dissolve what's left. And yet this hellscape was once almost identical to Earth. So what went wrong? What turned our twin planet into a cosmic torture chamber? And here is a question. If you could bring only one item to Venus to help you survive, what would it be? Comment down below. I will pin the most creative answer. Now let's begin. Why is Venus so impossibly hostile? The answer lies in a runaway greenhouse effect, the most extreme example we know of in the entire solar system. Venus is closer to the Sun than Earth, sure, about 72 million kilometers compared to Earth's 150 million. But that alone doesn't explain the inferno. Mercury is even closer to the Sun, and while its day side is scorching, its night side is freezing. Venus, on the other hand, maintains the same hellish temperature day and night, pole to pole. The reason is its atmosphere. Venus's atmosphere is 92 times thicker than Earth's. If you were standing on Venus, the pressure would be equivalent to being 3,000 feet underwater on Earth. Your body would be subjected to crushing forces from all directions. Your lungs would collapse. Your bones would fracture. You wouldn't just die, you'd be compressed into a much smaller, much denser version of yourself, but the pressure is only part of the nightmare. The atmosphere is 96% carbon dioxide. This creates a greenhouse effect so powerful that heat from the sun gets trapped and can never escape. The surface temperature doesn't just rise during the day and fall at night like it does on Earth. It stays constant. Constant heat, constant pressure, constant hell. The temperature on Venus is actually hotter than on Mercury, even though Mercury is closer to the Sun. Think about that. Distance from the Sun isn't the key factor, atmosphere is. And Venus's atmosphere is a textbook example of what happens when a greenhouse effect spirals completely out of control. Now, here's where it gets truly fascinating and terrifying. Venus wasn't always like this. Scientists believe that billions of years ago, Venus might have had oceans, liquid water oceans, just like Earth. The evidence comes from measurements of deuterium, a heavy isotope of hydrogen, in Venus's atmosphere. The ratio of deuterium to regular hydrogen on Venus is about 150 times higher than on Earth. This suggests that Venus once had significant amounts of water, but over time, that water was broken apart by ultraviolet radiation from the sun. The hydrogen escaped into space, leaving behind the heavier deuterium. What happened to the oceans? They boiled away, every drop, every molecule. Venus went from a potentially habitable world to an uninhabitable hellscape. And the question that keeps scientists awake at night is this: why did Venus turn into hell while Earth became a paradise? The answer likely involves a combination of factors. Venus's proximity to the Sun meant it received more solar radiation. This caused more water to evaporate, which increased the greenhouse effect. More greenhouse effect meant more heat, which caused even more water to evaporate. It was a vicious cycle, a feedback loop that couldn't be stopped. Eventually, all the water was gone, and carbon dioxide from volcanic eruptions built up in the atmosphere with nothing to remove it. On Earth, carbon dioxide gets absorbed by oceans and locked away in rocks through a process called the carbonate-silicate cycle. But without water, Venus had no way to regulate its carbon dioxide levels. The greenhouse effect ran wild, and the planet became the scorched wasteland we see today. Let's paint a picture of what you'd actually experience if you could somehow visit Venus's surface. You step out of your impossibly advanced spacecraft onto the rocky ground. Immediately, the pressure hits you like being at the bottom of the ocean. Your spacecraft's hull groans under the strain. The air, if you can call it that, is so thick it's almost liquid. It's hard to see more than a few hundred meters in any direction because the atmosphere scatters light in strange ways. The sky above is a murky orange-yellow, perpetually overcast with those sulfuric acid clouds. You can't see the sun, you can't see stars, just an oppressive glowing haze. The ground beneath your feet is volcanic basalt, dark and fractured. You're standing on a landscape shaped entirely by volcanism. There are no plate tectonics on Venus like we have on Earth. Instead, the entire surface seems to have been resurfaced by massive volcanic eruptions roughly 500 million years ago. Every crater, every mountain, every plain you see is younger than that. Venus essentially hit a reset button, burying its ancient history under fresh lava, and the volcanism might not be over. Recent observations from the European Space Agency's Venus Express mission and ground-based telescopes have detected fluctuations in sulfur dioxide levels in the atmosphere, suggesting that volcanoes might still be active today. If you're finding this fascinating, please give this video a like. It really helps me bring more cosmic mysteries to you. Now let's talk about the winds. On the surface of Venus, winds are gentle, only a few miles per hour. But high up in the atmosphere, at the cloud tops, winds scream around the planet at over 200 miles per hour. That's faster than the most powerful hurricanes on Earth. These super-rotating winds circle Venus in just 4 days, even though the planet itself takes 243 Earth days to complete one rotation. Yes, you heard that right. A day on Venus is longer than a year on Venus. Venus rotates so slowly and in the opposite direction from most planets that the sun rises in the west and sets in the east. And it takes longer for Venus to spin once on its axis than it does to orbit the sun. If you could stand on Venus and somehow survive, you'd experience a day-night cycle that lasts 117 Earth days. Why does Venus rotate backwards? Why does it spin so slowly? Scientists aren't entirely sure, but the leading theory involves a massive collision early in Venus's history. A planet-sized object might have smashed into Venus, altering its rotation. Or perhaps gravitational interactions with the sun and the thick atmosphere caused the rotation to slow down and reverse over billions of years. It's one of the many mysteries Venus still holds. Let's zoom out for a moment and think about what Venus tells us about planetary evolution and the possibility of life elsewhere. Venus is a cautionary tale. It shows us how thin the line is between a habitable world and a dead one. Earth and Venus started out similar. Both formed in the inner solar system from the same primordial material. Both likely had water. Both had volcanic activity. But something went wrong on Venus. Maybe it was just bad luck, being a bit too close to the sun. Maybe it was the absence of a large moon like Earth's, which helps stabilize our axial tilt and climate. Maybe it was the lack of plate tectonics, which on Earth helps recycle carbon and regulate temperature over geological timescales. Whatever the reason, Venus ended up on a different evolutionary path, and that path led straight to hell. This has profound implications for the search for life beyond our solar system. When astronomers discover exoplanets in the habitable zones of distant stars, planets that are roughly Earth-sized and at the right distance for liquid water, they get excited. And they should. But Venus reminds us that being in the habitable zone doesn't guarantee habitability. A planet can be the right size, at the right distance, and still become a nightmare world. Venus teaches us that atmospheres matter. Geological activity matters. The presence or absence of water matters. Every factor plays a role in determining whether a world becomes a cradle for life or a tomb. The story of Venus also connects to one of the biggest questions facing humanity today: climate change. Now, I'm not here to preach or get political. I'm here to share science, and the science is clear. Venus experienced a runaway greenhouse effect. Carbon dioxide built up in the atmosphere, trapping heat, raising temperatures, causing more carbon dioxide to be released from rocks and volcanoes. which trapped even more heat. It was an unstoppable spiral. Earth has its own carbon cycle, but human activities are releasing carbon dioxide at rates that could disrupt that cycle. We're not going to turn Earth into Venus. Let me be absolutely clear about that. Earth is farther from the Sun, has oceans, has life that absorbs carbon, and has geological processes that regulate climate over millions of years. But Venus shows us what happens when a greenhouse effect goes unchecked. It's a warning written in sulfuric acid clouds and molten landscapes. Ignore the lessons of Venus at your peril. Let's dive deeper into some of the specific features of Venus's surface, because despite the hellish conditions, we've managed to map almost the entire planet. How? Radar. In the early 1990s, NASA's Magellan spacecraft spent 4 years orbiting Venus, using radar to penetrate the thick clouds and create detailed maps of the surface. What Magellan revealed was astonishing. Venus has vast highland regions, enormous volcanic plains, and features unlike anything on Earth. There are pancake domes, circular volcanic structures that look like someone stacked giant pancakes on the landscape. There are coronae, massive circular features hundreds of miles across, caused by plumes of hot material rising from deep within the planet. There are tesserae, highly deformed regions of terrain that suggest intense geological stresses. One of the most prominent features is Ishtar Terra, a highland region about the size of Australia. Within Ishtar Terra rises Maxwell Montes, the tallest mountain on Venus, reaching over 7 miles above the planet's mean radius. That's taller than Mount Everest, though measuring mountains on Venus is tricky because there's no sea level to use as a reference point. Maxwell Montes is named after James Clerk Maxwell, the physicist who formulated the classical theory of electromagnetic radiation. It's the only feature on Venus not named after a woman. Almost every other geographical feature on Venus bears a female name, honoring goddesses and notable women from history and mythology. A poetic touch for a planet named after the goddess of love, even if the planet itself is anything but loving. Another fascinating feature is Aphrodite Terra, an enormous highland region that stretches nearly halfway around Venus's equator. It's about the size of Africa. Within Aphrodite Terra are some of the most complex geological structures on the planet, including Artemis Corona, one of the largest coronae on Venus, over 1,300 miles in diameter. These coronae are thought to form when hot magma rises from the mantle, pushing up the crust, then collapsing back down, leaving behind these circular scars. They're evidence of a geologically active interior, a planet that's still alive in some sense, even if its surface is dead. Speaking of geological activity, let's talk about Venus's volcanoes. There are more volcanoes on Venus than on any other planet in the solar system. Estimates suggest there are over 1,600 major volcanoes and possibly 1 million or more smaller ones. These aren't all active, but some might be. In 2020, scientists analyzing old data from the Magellan mission noticed that a volcanic vent changed shape between 2 images taken 8 months apart. The vent appeared to expand and fill with lava, suggesting an active eruption. Then, in 2023, researchers using archival data from NASA's Magellan and the Venus Express missions identified infrared hotspots that appeared and disappeared, consistent with fresh lava flows. This is exciting because active volcanism means Venus's interior is still hot, still churning, still geologically dynamic. But why does this matter? Because volcanism is often linked to habitability. On Earth, volcanic activity releases gases that help regulate the atmosphere, provides nutrients for life, and creates new land. If Venus has active volcanoes, it means the planet's interior hasn't completely cooled. And if the interior is still active, that opens intriguing questions about Venus's past and whether it could ever be habitable again. Probably not in the way we'd hope, but the universe loves to surprise us. If you're fascinated by the challenges of surviving on other planets, you should definitely check out my video called "What is actually preventing us from colonizing Mars?" In that video, I dive into the real obstacles we face when trying to make another planet our home. Many of the same challenges we see on Venus, like atmospheric composition, radiation, and temperature extremes, also apply to Mars, though in different ways. The video is in the description and on the card above. Back to Venus, let's talk about the clouds. Those beautiful, deadly clouds. The main cloud deck on Venus sits between 30 and 40 miles above the surface. It's made primarily of sulfuric acid droplets, with trace amounts of other compounds like hydrochloric acid and hydrofluoric acid. Just typing those words makes my skin crawl. The clouds are so reflective that they bounce back about 75% of the sunlight that hits them. That's why Venus shines so brightly in our sky. But above and below the main cloud deck, the atmosphere becomes even stranger. High above, at around 50 to 60 miles altitude, conditions are surprisingly mild. The temperature hovers around room temperature, roughly 75 degrees Fahrenheit, and the pressure is similar to Earth's surface. This region is sometimes called the habitable zone of Venus's atmosphere. In fact, some scientists have proposed that we could explore Venus not by landing on the surface, but by floating in the upper atmosphere. Imagined dirigibles, airships filled with breathable air, which would actually be a lifting gas on Venus because the atmosphere is so dense with carbon dioxide. These floating research stations could drift through the clouds, studying the atmosphere, searching for signs of chemistry that might hint at life. And yes, I said life. Because in 2020, a team of scientists led by Jane Greaves announced the detection of phosphine in Venus's atmosphere. Phosphine is a molecule made of one phosphorus atom and 3 hydrogen atoms. On Earth, it's associated with biological processes produced by anaerobic bacteria and industrial activity. Finding it on Venus was shocking. The discovery sparked intense debate. Could there be microbial life floating in the clouds of Venus? Life that evolved in the oceans billions of years ago and adapted to survive in the acidic cloud droplets as the surface became uninhabitable? It sounds like science fiction, but it's not impossible. Microbes on Earth can survive in incredibly extreme environments. We've found them in acid mines, in boiling hot springs, in frozen Antarctic lakes, even in the upper atmosphere. If life can adapt to those conditions on Earth, maybe, just maybe, it could adapt to Venus's clouds. But the phosphine detection has been challenged. Follow-up observations with different telescopes haven't consistently confirmed the signal. Some scientists argue that the original data was misinterpreted, that what looked like phosphine might actually be sulfur dioxide or some other molecule. Other researchers have proposed non-biological ways to produce phosphine on Venus, like volcanic activity or chemical reactions in the atmosphere. The debate is ongoing. New missions are planned to investigate. NASA's Da Vinci mission, short for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is set to launch in the late 2029 timeframe. It'll send a probe plunging through Venus's atmosphere, analyzing its composition with unprecedented precision. The European Space Agency's Envision mission will also study Venus, using radar and spectrometers to map the surface and atmosphere in detail. These missions will help answer the phosphine question and many others. Is there life on Venus? Is there active volcanism? What happened to the water? How did Venus become so different from Earth? The answers are waiting in that toxic sky, buried beneath those acid clouds, etched into the volcanic plains. Venus holds secrets about planetary evolution, about the limits of habitability, about the fine line between heaven and hell, and we're only just beginning to uncover them. Let's take a step back and think about the bigger picture. Venus is part of a family, our solar system, a collection of worlds that all formed from the same spinning disk of gas and dust roughly 4.6 billion years ago. Each planet took a different path. Mercury became a scorched, airless rock. Venus became a runaway greenhouse nightmare. Earth became a blue oasis teeming with life. Mars started wet and warm but lost its atmosphere and froze. The gas giants formed massive atmospheres and never developed solid surfaces. Each world is an experiment in planetary physics, chemistry, and geology. By studying Venus, we learn not just about Venus, but about how planets work in general. We learn about feedback loops, about atmospheric dynamics, about the role of water and carbon in regulating climate. This knowledge isn't just academic, it's practical. As we search for potentially habitable exoplanets around other stars, we need to know what to look for and what to avoid. We need to understand that a planet in the habitable zone might look promising from light years away, but could be a Venus-like hell up close. Telescopes like the James Webb Space Telescope are revolutionizing exoplanet science. Webb can analyze the atmospheres of distant worlds, looking for water vapor, carbon dioxide, methane, and other molecules. If we detect a thick carbon dioxide atmosphere on an Earth-sized exoplanet, Venus teaches us to be cautious. That planet might be beautiful from a distance but deadly up close. And here's something even more mind-blowing. Some scientists think Venus might go through cycles. The theory goes like this. Venus's thick crust builds up heat from the interior over hundreds of millions of years. Eventually, the pressure becomes too much, and the entire crust becomes unstable. Massive volcanic eruptions break out across the planet, resurfacing the entire world in a catastrophic event. This releases enormous amounts of heat and gas, then the crust solidifies again, and the cycle repeats. Evidence for this comes from the age of Venus's surface. Almost everything we see is between 300 million and 600 million years old. There are very few older features, suggesting that the entire surface was wiped clean in a global resurfacing event. If this theory is correct, Venus doesn't evolve gradually like Earth. It evolves in violent apocalyptic bursts. Imagine witnessing that. The entire planet convulsing, lava flooding across continents, the atmosphere choked with even more volcanic gases, temperatures spiking even higher. It's planetary rebirth through fire, and it could happen again. Maybe not in our lifetimes, maybe not for another 100 million years, but it's a reminder that planets are dynamic, living systems in their own right. They breathe, they change, they die, and sometimes they're reborn. Now let's talk about something that often gets overlooked: Venus's lack of a magnetic field. Earth has a strong magnetic field generated by the movement of molten iron in our outer core. This magnetic field acts like a shield, deflecting charged particles from the solar wind and protecting our atmosphere from being stripped away. Mars once had a magnetic field, but it shut down billions of years ago, and the solar wind has been slowly eroding Mars's atmosphere ever since. Venus never developed a strong magnetic field, or if it did, it lost it early in its history. Without this protection, the solar wind has been pounding Venus's atmosphere for billions of years. But here's the twist. Venus's atmosphere is so thick that it doesn't need a magnetic field for protection. The sheer mass of the atmosphere, 92 times denser than Earth's, creates its own barrier. The solar wind does strip away some of the upper atmosphere, but the lower atmosphere remains intact. It's a different kind of protection, brute force rather than elegance. Earth's magnetic field is like a fencer's parry, redirecting the solar wind around the planet. Venus's thick atmosphere is like a fortress wall, absorbing the blows through sheer mass. The absence of a magnetic field also tells us about Venus's interior. Magnetic fields are generated by dynamos, the movement of conductive fluids in a planet's core. Earth's core is partially liquid, churning and convecting, generating our magnetic field. Venus's lack of a magnetic field suggests its core might be fully solid, or that it lacks the convection necessary to generate a dynamo. This in turn tells us about the planet's thermal history. Venus might have cooled differently than Earth, or its interior structure might be fundamentally different. Scientists are still piecing together the puzzle. Let's talk about transits. A transit occurs when a planet passes directly between Earth and the Sun, appearing as a tiny black dot moving across the Sun's face. Venus transits are rare and spectacular events. They occur in pairs 8 years apart, then don't happen again for over a century. The last pair of Venus transits occurred in 2004 and 2012. The next won't happen until 2117 and 2125. So if you missed the 2012 transit, you're out of luck for over a century. Sorry. Transits of Venus have played a crucial role in the history of astronomy. In the 18th and 19th centuries, astronomers organized global expeditions to observe Venus transits from different locations on Earth. By timing exactly when Venus appeared to cross the Sun's disk from different vantage points, they could use parallax to calculate the distance from Earth to the Sun. This measurement, called the astronomical unit, became the foundation for measuring distances throughout the solar system and beyond. Captain James Cook's first voyage to the Pacific in 1769 was primarily to observe the transit of Venus from Tahiti. So Venus transits aren't just beautiful celestial events. They're scientific milestones that helped us understand our place in the cosmos. Speaking of our place in the cosmos, let's zoom out even further. Venus is a reminder that we live in a Goldilocks zone, not just in terms of distance from the Sun, but in terms of countless other factors. Earth has the right mass to hold an atmosphere, but not so much that it becomes oppressive. We have liquid water on the surface, we have a magnetic field, we have plate tectonics, we have a large moon that stabilizes our axial tilt. We have Jupiter in the outer solar system, acting as a gravitational vacuum cleaner, sweeping up asteroids and comets that might otherwise bombard Earth. Every one of these factors contributes to making Earth habitable. Change any one of them significantly, and Earth might look very different. It might look like Venus. This realization should fill you with both wonder and responsibility. Wonder because we're incredibly fortunate to exist on a planet that threads the needle of habitability. Responsibility because that habitability isn't guaranteed forever. Earth's climate has changed dramatically over geological time. We've had ice ages and hothouse periods. We've had mass extinctions and evolutionary explosions. The planet is resilient, but it's not invincible. Venus is a warning of what can happen when a climate system spirals out of control. It's a lesson written in the sky, visible to anyone who looks up after sunset or before dawn. Let's bring this back to you, the viewer. You're made of stardust. Every atom in your body, every carbon atom, every oxygen atom, every atom of iron in your blood was forged in the heart of a dying star billions of years ago. Those stars exploded in supernovae, scattering their enriched material into space. That material coalesced into new stars, new planets, and eventually, you. You are literally the universe experiencing itself. And when you look at Venus, you're looking at a world made of the same stardust, a sibling planet that took a different path. Venus could have been Earth. Earth could have been Venus. The difference is a matter of chance, physics, and billions of years of complex interactions. This connection between us and the cosmos isn't just poetic. It's literal. Understanding Venus helps us understand ourselves. It helps us appreciate the fragility and preciousness of our world. It helps us see that we're not separate from the universe. We're part of it, woven into its grand story, participants in an adventure that's been unfolding for 13.8 billion years since the Big Bang. Now let's talk about some of the bizarre phenomena that occur on Venus. One of the strangest is the superrotation of the atmosphere I mentioned earlier. The entire atmosphere whips around the planet in just 4 Earth days, 60 times faster than the planet itself rotates. This is still not fully understood. On Earth, atmospheric circulation is driven by the planet's rotation and the heating from the sun, creating trade winds, jet streams, and weather patterns. But Venus rotates so slowly that this mechanism shouldn't work the same way. Yet somehow the atmosphere has decoupled from the surface and spins independently at incredible speeds. Scientists think it might be related to the way heat is distributed in the thick atmosphere, creating powerful convection currents and waves that transfer momentum. But the exact mechanisms are still being researched. Another weird feature is the vortex at each of Venus's poles. Imagine a massive hurricane that never moves, permanently stationed over the pole, with swirling clouds forming a strange eye-like structure. These polar vortices were discovered by the Pioneer Venus mission in the late 1970s and have been studied by subsequent missions. They're not like Earth's polar vortices, which are relatively stable wind patterns. Venus's polar vortices are chaotic, constantly changing shape, sometimes appearing as a single eye, sometimes splitting into multiple swirls. They're driven by the super-rotating winds converging at the poles, creating turbulent, beautiful, and utterly alien structures. Lightning on Venus is another mystery. Early missions detected what appeared to be radio signals consistent with lightning strikes. But unlike Earth, where lightning is associated with thunderstorms and water clouds, Venus's lightning seems to occur in the sulfuric acid clouds. Some scientists have proposed that the lightning might be triggered by volcanic eruptions, with ash particles colliding and generating static electricity. Others suggest it could be a different kind of electrical discharge, unique to Venus's dense, acidic atmosphere. The Venus Express mission found some evidence of lightning, but the signals were faint and hard to confirm. Future missions will hopefully settle this question. Does Venus crackle with electrical storms beneath those toxic clouds? We'll find out soon. Let's talk about the wind patterns in more detail. On the surface, as I mentioned, winds are gentle, just a few miles per hour. But because the atmosphere is so dense, even these gentle winds carry tremendous force. If you tried to walk through them, it would feel like pushing through water. The slow surface winds are caused by the thick atmosphere and slow rotation. There's simply not much to drive fast surface winds, but as you climb higher into the atmosphere, the winds accelerate. At the cloud tops, they reach over 220 miles per hour. These winds create massive planet-spanning waves in the clouds, visible from orbiting spacecraft. The clouds form long, streaky patterns racing around the planet, driven by forces we're still working to fully understand. One of the most intriguing aspects of Venus's atmosphere is its chemistry. In addition to carbon dioxide and sulfuric acid, the atmosphere contains trace amounts of water vapor, carbon monoxide, sulfur dioxide, and other compounds. The chemistry is complex and dynamic, with reactions occurring at different altitudes, driven by temperature, pressure, and sunlight. High in the atmosphere, ultraviolet light from the sun breaks apart molecules, creating reactive fragments that recombine in unexpected ways. Lower down, chemical reactions occur in the sulfuric acid clouds, potentially creating exotic compounds that don't exist on Earth. Some scientists have speculated that these reactions could produce organic molecules, the building blocks of life, even in the absence of biology. It's a chemical laboratory unlike anywhere else in the solar system. Now, let's discuss the surface in more detail. If you could somehow survive on Venus's surface and look around, you'd see a world dominated by volcanic features. There are shield volcanoes, similar to those in Hawaii, with broad, gently sloping sides built up by repeated lava flows. There are stratovolcanoes, steeper and more cone-shaped. There are lava channels, some stretching for hundreds of miles, carved by rivers of molten rock. One of the longest lava channels in the solar system, Baltis Vallis, stretches over 4,000 miles across Venus's surface. That's longer than the Nile River. Imagine a river of lava, glowing red-hot, flowing across a landscape for thousands of miles. It's a vision of hell made real. The rocks on Venus's surface are basaltic, similar to the rocks that make up Earth's oceanic crust and volcanic islands. We know this from the Soviet Venera landers, which analyzed rock samples and sent back data before succumbing to the heat. The rocks are dark, rough, and fractured, shaped by volcanic eruptions and the intense surface conditions. Some areas show evidence of weathering, not from water or wind like on Earth, but from chemical reactions with the atmosphere. The rocks react with sulfur compounds, creating minerals that might not exist anywhere else. Venus is literally creating new chemistry, new mineralogy through its extreme conditions. One of the most haunting aspects of the Venera missions is the images they sent back. These grainy, orange-tinted photographs show a barren, rocky landscape under a dim, hazy sky. The horizon is close because Venus is slightly smaller than Earth, and the thick atmosphere bends light in strange ways. There are no mountains in the distance, no vegetation, no signs of life. Just rocks and more rocks, stretching to the horizon under that oppressive, glowing sky. These images are the only photographs we have from the surface of Venus, and they'll likely remain the only ones for a long time. Future missions are planned, but landing on Venus is so difficult and expensive that it's not a priority compared to other targets like Mars, the moons of Jupiter and Saturn, and asteroids. But there's something profoundly moving about those images. They show a world so close to ours in space, yet so different in character. A world that could have been our twin, but instead became our opposite. They remind us that the universe doesn't guarantee happy endings. Planets don't always evolve toward habitability. Sometimes they evolve toward destruction. And yet, those images also inspire awe, because despite the hellish conditions, we managed to get there. We built machines tough enough to survive, even briefly, on the surface of another planet. We sent our robotic emissaries across millions of miles of space to touch another world and send back a message. We were here, we saw this, we learned. Let's talk about the future of Venus exploration. I mentioned Da Vinci and Envision, but there are other concepts in development. NASA has also selected the Veritas mission, which stands for Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy. Veritas will use radar to create high-resolution maps of Venus's surface, study its geology, and search for signs of active volcanism and tectonics. The mission was delayed due to budget constraints, but it's still on the books for a potential launch in the early 2031 timeframe. Meanwhile, India's space agency, ISRO, is developing a mission called Shukrayan, which means Venus craft in Sanskrit. Russia has proposed Venera D, a successor to the legendary Venera missions, which would include an orbiter, a lander, and possibly atmospheric balloons or drones. These missions represent a renewed interest in Venus, a recognition that we've neglected this planet for too long. Why the renewed interest? Several reasons. First, the potential phosphine detection sparked excitement and debate. If there's even a slim chance of life in Venus's clouds, we need to investigate. Second, Venus is a laboratory for studying extreme climate and atmospheric processes. Understanding Venus helps us understand Earth's climate and predict how it might change. Third, Venus is relatively close. It's easier to reach than the outer planets, making it an attractive target for missions on limited budgets. Fourth, technology has advanced. We can build electronics that survive higher temperatures, develop better heat shields, and design missions that can operate in Venus's brutal environment for longer periods. One of the most exciting proposals is the concept of aerial platforms. Instead of trying to survive on the surface, these missions would float in the upper atmosphere, where conditions are much more benign. Imagine a solar-powered aircraft soaring through Venus's clouds at 50 miles altitude, sampling the atmosphere, studying the chemistry, searching for signs of life. Or picture a balloon-based observatory drifting with the super-rotating winds, circling the planet every 4 days, monitoring weather patterns and volcanic activity. These missions could operate for months or even years, providing continuous data from an environment we've barely explored. Some visionaries have even proposed colonizing Venus's upper atmosphere. The idea sounds insane at first, but hear me out. At an altitude of 50 miles, the temperature is comfortable, the pressure is similar to Earth's surface, and the atmosphere protects you from radiation. You'd need to deal with the sulfuric acid, of course, but that's a solvable engineering problem. You could build floating cities, massive structures filled with breathable air, which would naturally float in the dense carbon dioxide atmosphere. Solar panels would provide abundant energy because Venus receives more sunlight than Earth. You'd extract carbon dioxide from the atmosphere and use it to produce food through agriculture or chemical synthesis. Water would be scarce, but you could extract trace amounts from the atmosphere or bring it from elsewhere. Is this realistic? Maybe not in the near future. We have more pressing priorities, like establishing a presence on the Moon and Mars. But in the long term, centuries from now, floating cities on Venus could become reality. It's a reminder that even the most hostile environments might be colonized if we're clever enough, patient enough, and determined enough. Venus challenges us to think beyond traditional notions of habitability, to imagine new ways of living in space. Now let's circle back to the question that haunts every discussion of Venus. Could it have harbored life in the past? We've talked about the evidence for ancient oceans. If Venus had liquid water for hundreds of millions or even billions of years, that's enough time for life to emerge. Life on Earth appeared relatively quickly, within the first billion years of our planet's history. The basic ingredients, liquid water, organic molecules, and energy sources, were all present on early Venus. So it's not unreasonable to think that life could have started there. But what happened to it? If Venus once had oceans and life, where did it go? The most likely scenario is that as the oceans evaporated and the greenhouse effect intensified, any surface life would have perished. The temperatures rose too high, the water disappeared, and the environment became sterilized. But could some organisms have adapted? Could they have evolved to survive in the atmosphere, floating in the clouds as the surface became uninhabitable? It's a fascinating idea. On Earth, we have microbes that live in clouds, surviving in tiny water droplets, reproducing and spreading through the atmosphere. Could Venus harbor similar organisms, descendants of ancient surface life, now adapted to an aerial existence? This is pure speculation, of course. We have no evidence of life on Venus, past or present, but the possibility is tantalizing enough to warrant investigation. The phosphine detection, controversial as it is, has opened the door to serious scientific discussion about Venusian life. Future missions will search for biosignatures, chemical or physical signs that could indicate biological activity. They'll analyze the cloud particles, looking for organic molecules, patterns of chemistry that don't fit non-biological explanations. They'll study the isotopic ratios of elements, searching for the telltale fingerprints of metabolism. Even if we don't find life, the search itself is valuable. It pushes the boundaries of our understanding. It forces us to think about what life is, where it can exist, and how it adapts. It reminds us that the universe is stranger and more diverse than we imagine. Every world we study expands our perspective, challenges our assumptions, and reveals new possibilities. Let's talk about Venus's role in human culture and mythology. As I mentioned earlier, Venus is named after the Roman goddess of love and beauty, but the planet has been observed and revered by cultures around the world for thousands of years. The ancient Babylonians called it Ishtar, after their goddess of love and war. The ancient Greeks, initially, thought Venus was two different objects, calling the morning appearance Phosphorus and the evening appearance Hesperus, before realizing they were the same planet. The Maya civilization tracked Venus with incredible precision, incorporating its cycles into their calendars and religious practices. They associated Venus with warfare and used its appearances to time military campaigns. In more recent history, Venus has captured the imagination of science fiction writers. Before we knew the true conditions on Venus, authors imagined it as a lush, tropical world covered in jungles and oceans, possibly inhabited by exotic life forms. Stories depicted Venus as a prehistoric paradise, a younger version of Earth. When space probes revealed the reality, a scorched, toxic wasteland, it was a shock, but it also inspired a new kind of story, tales of survival against impossible odds, of terraforming projects to transform Venus into a habitable world, of the tragedy of a planet that could have been our twin. Terraforming Venus is a concept that's been explored both in fiction and serious scientific proposals. The idea is to deliberately engineer Venus's environment to make it habitable for humans. How would you do this? The most common proposal involves removing or sequestering the carbon dioxide in the atmosphere. You could introduce genetically engineered bacteria or algae that consume carbon dioxide and produce oxygen, similar to what happened on early Earth. You could use massive solar shades to block sunlight, cooling the planet and allowing the carbon dioxide to condense and precipitate out. You could bombard Venus with icy asteroids or comets, adding water and helping to cool the atmosphere. Over centuries or millennia, you might gradually transform Venus from a hellish greenhouse into a more temperate world. Is this feasible? With current technology, absolutely not. The scale of the project would be mind-boggling, requiring resources and coordination far beyond anything humanity has ever attempted. But in the distant future, with advanced technology and abundant energy, terraforming Venus might become possible. It would take thousands of years, maybe tens of thousands, but it's not physically impossible, just incredibly difficult, and it raises profound ethical questions. Do we have the right to fundamentally alter another planet? What if there is life in the clouds? Would terraforming Venus destroy it? These are questions we'll need to grapple with if we ever become a truly spacefaring civilization. For now, Venus remains what it is, a natural laboratory, a cautionary tale, and a reminder of the diversity of planetary outcomes. It's a world that defies easy categorization, a planet that looks beautiful from a distance but reveals its true nature only upon close inspection. In many ways, Venus embodies the duality of the cosmos itself, beauty and terror, familiarity and alienness, hope and warning, all wrapped into one brilliant point of light in our sky. Let's delve into some of the specific scientific discoveries that have shaped our understanding of Venus. One of the most important came from the Mariner 2 mission in 1962, the first successful interplanetary mission in history. Mariner 2 flew past Venus and confirmed what many scientists suspected. The planet was incredibly hot, with surface temperatures far exceeding the boiling point of water. This discovery shattered the romantic visions of a tropical paradise and forced scientists to rethink planetary atmospheres and greenhouse effects. It was a watershed moment in planetary science, proving that we could send spacecraft to other worlds and return data that fundamentally changed our understanding. The Soviet Venera program, which ran from the 1960s through the 1980s, was an engineering marvel. The Soviets designed landers specifically to survive Venus's extreme conditions, using thick pressure vessels, heat shields, and refrigeration systems. The first successful landing was Venera 7 in 1970, which transmitted data for 23 minutes from the surface. Subsequent missions improved on this, with Venera 9 and Venera 10 sending back the first photographs from another planet's surface in 1975. Venera 13 and Venera 14, which landed in 1981 and 1982, survived for over 2 hours and returned color images showing the rocky volcanic landscape in vivid detail. These missions were triumphs of human ingenuity. Consider the engineering challenges. You're designing a spacecraft to land on a world where the temperature is hot enough to melt lead, the pressure is crushing, and the atmosphere is full of corrosive acids. Your spacecraft has to survive the journey through space, endure a fiery descent through the thick atmosphere, land safely on rough terrain, deploy instruments, and transmit data back to Earth, all before the heat overwhelms your systems. The fact that the Soviets succeeded multiple times is astonishing. It's a testament to what we can achieve when we commit to exploration, when we refuse to accept the limitations of the present and push the boundaries of what's possible. NASA's Magellan mission, which orbited Venus from 1990 to 1994, revolutionized our understanding of the planet's geology. Using synthetic aperture radar, Magellan mapped 98% of Venus's surface at a resolution better than any previous mission. The data revealed a world shaped by volcanism and tectonics, with impact craters that provided clues about the age of the surface. Magellan also measured tiny variations in Venus's gravity field, which told us about the structure of the interior. The mission confirmed that Venus has a metallic core, a rocky mantle, and a crust similar to Earth's internal structure. But the lack of plate tectonics meant that heat escapes differently, possibly through the catastrophic resurfacing events I mentioned earlier. The European Space Agency's Venus Express, which orbited the planet from 2006 to 2014, focused on the atmosphere and upper layers. It studied the superrotation, analyzed the composition of the clouds, observed the polar vortices, and searched for signs of lightning and volcanic activity. Venus Express confirmed that Venus is losing water to space. The solar wind strips away hydrogen and oxygen atoms from the upper atmosphere, carrying them off into space. Over billions of years, this process has removed vast amounts of water, contributing to Venus's dry state. It's a slow, relentless process, a reminder that atmospheres aren't permanent. They evolve, they leak away, they change over geological time. Japan's Akatsuki spacecraft, which has been orbiting Venus since 2015, has provided new insights into atmospheric dynamics. Akatsuki carries cameras that observe Venus at different wavelengths, revealing temperature variations, cloud structures, and wind patterns. One of Akatsuki's most exciting discoveries was the detection of a massive bow-shaped wave in the atmosphere, stretching across almost the entire planet. This stationary wave, similar to gravity waves on Earth, is thought to be caused by mountains on the surface disturbing the flow of the super-rotating winds. It's like an atmospheric standing wave, a ripple frozen in the sky, created by the interaction between the solid planet below and the fluid atmosphere above. Akatsuki also observed rapid changes in wind speeds and temperature, revealing that Venus's atmosphere is even more dynamic and turbulent than previously thought. These missions have painted a detailed picture of Venus, but they've also raised new questions. Why doesn't Venus have plate tectonics? On Earth, plate tectonics is driven by convection in the mantle, with hot material rising and cool material sinking, creating a cycle that moves continents, builds mountains, and recycles the crust. Venus's interior should be hot enough for convection, so why don't we see plates? One theory is that Venus's crust is too dry. On Earth, water in the crust acts like a lubricant, allowing plates to slide past each other. Without water, Venus's crust might be too stiff, preventing plate motion. Instead, heat builds up until the entire crust becomes unstable and resurfacing occurs. It's a different tectonic regime, one we're still trying to understand. Another mystery is Venus's rotation. Why does it rotate so slowly, and why backward? Several theories have been proposed. One is that Venus originally rotated normally but was hit by a massive object early in its history, an impact so large that it flipped the planet's rotation. Another theory is that tidal interactions with the Sun gradually slowed Venus's rotation over billions of years. The thick atmosphere might also play a role, creating drag that affects the planet's rotation rate. Or perhaps Venus's rotation is chaotic, influenced by complex interactions between the core, mantle, crust, and atmosphere. We don't have a definitive answer yet, but ongoing research and future missions should help solve this puzzle. Let's talk about what Venus can teach us about exoplanets. Thanks to missions like Kepler, TESS, and now the James Webb Space Telescope, we've discovered thousands of planets orbiting other stars. Many of these are rocky worlds similar in size to Earth or Venus. Some are in the habitable zone, where temperatures might allow liquid water, but as Venus shows us, being in the habitable zone doesn't guarantee habitability. A planet can have the right size and distance, but still be uninhabitable due to its atmosphere, rotation, geological activity, or other factors. When astronomers study exoplanet atmospheres, they look for biosignatures, molecules that might indicate life, like oxygen, methane, or ozone. But they also need to consider false positives, non-biological processes that could produce the same molecule. Venus is a perfect example. If we detected carbon dioxide and sulfur compounds in an exoplanet's atmosphere, we might think it's a volcanic world like Venus. If we detected trace amounts of phosphine, we might get excited about potential life, but we'd need to rule out other explanations first. Venus teaches us to be cautious, to consider multiple scenarios, and to gather as much data as possible before drawing conclusions. There's a particular class of exoplanets that might be Venus-like worlds. Astronomers have identified super-Earths and mini-Neptunes in close orbits around their stars, receiving intense radiation and likely experiencing runaway greenhouse effects. Some of these planets might have thick carbon dioxide atmospheres, sulfuric acid clouds, and surface temperatures hot enough to melt metal. They're Venus's cousins, scattered across the galaxy, each one a unique variation on the theme of planetary hell. By studying these worlds, we can test our theories about atmospheric evolution, greenhouse effects, and the factors that determine habitability. One of the most exciting prospects is the possibility of finding an exo-Venus in transition, a planet that's currently losing its oceans and spiraling into a runaway greenhouse state. Imagine observing a world in real time as it transforms from potentially habitable to hellish. We could watch the process unfold over decades or centuries, gathering data that would illuminate the mechanisms driving the change. It would be like having a time machine, allowing us to see what Venus might have looked like billions of years ago as it lost its water and became the inferno we see today. This brings us to an important point about planetary science in general. Every planet tells a story. Earth tells a story of life, adaptation, and resilience. Mars tells a story of lost potential, of a world that once had rivers and lakes but lost its atmosphere and froze. Jupiter tells a story of failed stardom, a giant planet that never quite gathered enough mass to ignite fusion. Saturn tells a story of rings and moons, of a system rich in diversity and beauty. And Venus tells a story of runaway climate change, of a world that crossed a threshold and couldn't come back. Each story informs our understanding of how planets work, how they evolve, and what makes them unique. The solar system is our laboratory. We can't yet travel to exoplanets to study them up close, so we study the worlds in our own cosmic backyard and extrapolate outward. Venus is one of our most valuable test cases precisely because it's so different from Earth. It shows us what happens when things go wrong, when positive feedback loops spiral out of control, when a planet loses its balance. This isn't just abstract knowledge, it has practical implications for our own planet. Earth's climate is currently changing due to human activities. We're pumping carbon dioxide into the atmosphere at unprecedented rates, trapping heat, raising temperatures, melting ice, and altering weather patterns. Now, to be clear, Earth is not going to become Venus. We don't have enough carbon to create a runaway greenhouse effect of that magnitude. Our sun is not hot enough, our planet is not close enough, and our oceans won't completely evaporate. But we can create serious problems for ourselves and future generations. We can raise temperatures enough to disrupt agriculture, flood coastal cities, and trigger mass extinctions. Venus is not a prediction of Earth's future, but it is a warning about the power of greenhouse gases and the importance of maintaining atmospheric balance. Scientists use Venus as a model to test our understanding of climate physics. If our climate models can successfully explain Venus's extreme greenhouse effect, its super-rotating atmosphere, and its temperature distribution, then we can have more confidence in those models when applied to Earth. Conversely, if our models fail to explain Venus, we need to improve them. Venus is a stress test for climate science. Pushing our theories to the extreme and revealing their limitations, let's talk about some of the smaller mysteries and curiosities of Venus. For example, did you know that Venus has a tail? Not a physical tail like a comet, but a magnetic tail. Even though Venus doesn't have a global magnetic field, the solar wind interacts with the planet's ionosphere, the upper layer of the atmosphere where atoms are ionized by solar radiation. This interaction creates a bow shock, a region where the solar wind is deflected around the planet, and a magnetotail, a long streamer of charged particles stretching away from the sun. This magnetotail extends for millions of miles into space, creating a complex and dynamic environment that scientists are still studying. Another curiosity is the ashen light, a faint glow that some observers have reported seeing on the night side of Venus. When Venus is in a crescent phase, like the Moon, the dark side should be completely invisible. But for centuries, astronomers have occasionally reported seeing a faint, ghostly glow illuminating the night side. The ashen light is controversial because it's difficult to observe and even harder to explain. Some think it might be an optical illusion or scattered light from the bright day side. Others have proposed that it could be lightning, air glow from chemical reactions in the atmosphere, or even auroras caused by the interaction with the solar wind. No one knows for sure. It's one of those tantalizing mysteries that adds to Venus's enigmatic character. Venus also has tessera terrain, highly deformed regions of the crust that are unlike anything else on the planet. Tesserae are characterized by complex patterns of ridges and valleys, suggesting they've been subjected to intense tectonic forces. They're some of the oldest features on Venus, survivors from whatever global resurfacing event wiped out most of the ancient crust. Studying tesserae might give us clues about Venus's early history, about what the planet was like before the resurfacing event, and about the tectonic processes that shaped it. They're like geological fossils, preserving information about a lost world. One of the most intriguing aspects of Venus's geology is the coronae, circular or oval structures hundreds of miles across, surrounded by concentric ridges and fractures. Coronae are thought to be formed by upwelling plumes of hot material from deep in the mantle. The plume rises, pushes up the crust, creating a dome. Then as it cools and sinks back down, the crust collapses, forming the characteristic circular pattern. Earth has similar features called hot spots, like the one that created the Hawaiian Islands. But Venus's coronae are larger and more numerous, suggesting that the planet's interior convection might work differently than Earth's. Some coronae show signs of recent activity, with fresh lava flows and minimal weathering, hinting that Venus's volcanic system might still be active today. Speaking of volcanism, let's talk about some specific volcanoes. Mount Mons, which I mentioned earlier, is the tallest volcano on Venus, rising about 5 miles above the surrounding plains. It's a massive shield volcano with gently sloping sides and a summit caldera, a collapsed crater at the top. Mount Mons shows evidence of relatively recent lava flows, dark streaks that appear fresh compared to the surrounding terrain. Some scientists think Mount Mons might still be active, possibly erupting within the last few million years or even more recently. Sapers Mons is another large volcano about 250 miles across, with multiple overlapping lava flows creating a complex, layered structure. Sapers Mons has 2 distinct summit calderas, suggesting multiple phases of volcanic activity. The lava flows extend for hundreds of miles in all directions, blanketing the surrounding terrain in volcanic rock. Then there's Sif Mons, named after a Norse goddess, which rises about 1.5 miles above the plains and spans about 200 miles across. Sif Mons is notable for its bright summit, which appears different from the surrounding terrain in radar images. This brightness might indicate different rock types, different surface roughness, or different weathering, but the exact cause is still debated. These volcanoes are not just geological features. They're windows into Venus's interior, markers of where heat and material rise from deep below the surface. By studying their distribution, their ages, and their structures, scientists can infer how Venus's mantle convects, how the crust responds to internal forces, and how volcanic activity has shaped the planet over time. Let's shift gears and talk about observing Venus from Earth. As I mentioned, Venus is incredibly bright, easily visible to the naked eye, and often the first star to appear after sunset or before sunrise. With binoculars or a small telescope, you can see Venus's phases, just like the Moon's. When Venus is on the far side of the Sun from Earth, it appears full and small. As it moves closer to Earth, it appears larger but shows a gibbous phase, then a half phase, then a crescent. At its closest approach to Earth, Venus is a large, thin crescent, stunningly beautiful through a telescope. Observing Venus is one of the pleasures of amateur astronomy. Unlike many deep sky objects that require dark skies and large telescopes, Venus is bright enough to see even from light-polluted cities. You can track its motion against the background stars, watch its phases change over weeks and months, and marvel at its brilliance. It's a reminder that you don't need expensive equipment to connect with the cosmos. Sometimes the most spectacular sights are right there in front of you. visible to anyone who takes the time to look up. For professional astronomers, Venus presents unique challenges. Because it's so close to the Sun in the sky, it's difficult to observe with large telescopes. The risk of accidentally pointing a telescope at the Sun and damaging equipment or eyes means that Venus observations require careful planning and safety measures. Most detailed studies of Venus come from space-based telescopes or specialized instruments that can observe during twilight or use filters to block the Sun's glare. One fascinating aspect of Venus observation is the study of its phases by historical astronomers. Galileo Galilei was the first to observe Venus's phases with a telescope in 1610. This observation was crucial evidence for the heliocentric model of the solar system, the idea that planets orbit the Sun rather than Earth. In the geocentric model, where Earth is at the center and everything orbits around it, Venus should never show a full range of phases. But Galileo observed that Venus does go through all phases, from full to new, proving that it must orbit the Sun. This simple observation helped overturn centuries of astronomical dogma and paved the way for our modern understanding of the solar system. Transits of Venus are another historically significant phenomenon. A transit occurs when Venus passes directly between Earth and the Sun, appearing as a small black dot crossing the Sun's face. Transits of Venus are rare, occurring in pairs 8 years apart, with over a century between each pair. The last pair occurred in 2004 and 2012. The next won't happen until 2117 and 2125. Historically, transits of Venus were used to calculate the distance from Earth to the Sun, a measurement called the astronomical unit. By observing a transit from different locations on Earth, astronomers could use parallax, the apparent shift in Venus's position against the Sun, to triangulate the distance. These measurements were crucial for understanding the scale of the solar system and laid the groundwork for modern astronomy. The expeditions to observe Venus transits in the 18th and 19th centuries were major scientific undertakings. Astronomers traveled to remote corners of the Earth, from the Arctic to the South Pacific, enduring harsh conditions and dangerous journeys to observe these rare events. Captain James Cook's first voyage to Tahiti in 1769 was partly motivated by the desire to observe a Venus transit. These expeditions exemplified the international cooperation and dedication that characterize scientific exploration. They showed that humanity could work together across borders and cultures, united by curiosity and the desire to understand our place in the universe. Let's talk about the cultural impact of Venus beyond astronomy. Venus has influenced art, literature, music, and religion for millennia. In classical art, Venus, the goddess, is depicted as a symbol of beauty, love, and desire. Botticelli's The Birth of Venus is one of the most famous paintings in Western art, showing the goddess emerging from the sea on a shell. The painting captures an idealized vision of beauty, grace, and purity, qualities that have been associated with Venus for thousands of years. In literature, Venus has been a recurring motif. Shakespeare referenced Venus and Adonis in his poetry. Dante mentioned Venus in the Divine Comedy. Science fiction authors have imagined Venus as everything from a prehistoric jungle to a toxic wasteland. Ray Bradbury's The Long Rain depicts Venus as a world of endless rain and oppressive humidity, a far cry from the reality, but capturing the sense of Venus as an alien and hostile environment. In music, composers have written pieces inspired by Venus. Gustav Holst's suite, The Planets, includes a movement called Venus, the bringer of peace, which evokes a sense of serenity and beauty through gentle, flowing melodies. The contrast between this musical portrait and the reality of Venus is striking, but it reflects the duality of Venus as both a beautiful object in the sky and a terrifying world up close. In religion and mythology, Venus has been worshipped or revered by cultures around the world. The ancient Maya believed Venus was associated with warfare and used its appearances to schedule battles and rituals. The ancient Greeks associated Venus with Aphrodite, the goddess of love. The Romans continued this association with their goddess Venus. In Hindu astronomy, Venus is called Shukra, associated with wealth, luxury, and the arts. This cross-cultural significance shows that Venus has always captured human imagination, inspiring both scientific inquiry and spiritual contemplation. Now, let's return to science and discuss some of the most pressing questions that future missions hope to answer. First, is Venus volcanically active today? We have suggestive evidence, variations in sulfur dioxide levels, fresh-looking lava flows, possible thermal anomalies, but we need direct confirmation. A mission that could detect volcanic eruptions in real time, perhaps through seismic monitoring or infrared imaging, would revolutionize our understanding of Venus's interior and geological processes. Second, what is the detailed composition of Venus's atmosphere, particularly in the clouds where the phosphine detection was claimed? We need high-precision measurements of trace gases, isotopic ratios, and organic molecules. This will require instruments that can sample the atmosphere directly, analyzing it for chemical signatures that might indicate biological or geological processes we don't yet understand. Third, what is the structure and composition of Venus's crust in different regions? We know the general chemistry from the Venera landers, but we need more detailed analysis. Are there different rock types in the highlands versus the plains? Do the tesserae have a different composition that might tell us about Venus's early history? Future landers with advanced instruments could answer these questions. Fourth, what is the history of water on Venus? Did Venus have oceans, and if so, for how long? When and how did it lose its water? Studying the isotopic ratios of hydrogen and oxygen, analyzing mineral formations that might have been created in the presence of water, and mapping ancient shorelines if they exist would help reconstruct Venus's watery past. Fifth, why doesn't Venus have a magnetic field? We understand the basics. The slow rotation probably prevents the dynamo effect that generates Earth's magnetic field, but the details are unclear. Does Venus's core have the right composition and temperature to generate a magnetic field if it rotated faster? Or are there other factors at play? Understanding this could tell us about planetary interiors and magnetic field generation in general. Sixth, what drives the superrotation of Venus's atmosphere? We have theories involving atmospheric waves, heat distribution, and momentum transfer, but we need more detailed observations to test these theories. A mission with multiple atmospheric probes at different altitudes and latitudes could track wind patterns and temperature variations, helping us solve this puzzle. These questions are interconnected. Understanding Venus's volcanism helps us understand its interior structure, which relates to its magnetic field. Understanding its atmospheric composition helps us understand its climate history, which relates to the question of water and potential past habitability. Venus is a complex system, and unraveling its mysteries requires a holistic approach, combining geology, atmospheric science, chemistry, and physics. The upcoming missions, Da Vinci, Veritas, and Envision, are designed to address these questions from multiple angles. Da Vinci will drop a probe through the atmosphere, measuring composition and temperature as it descends, and will use imaging to map the surface in visible light for the first time. Veritas will use radar to create high-resolution maps and measure surface temperatures, searching for active volcanoes. Envision will study the subsurface structure using ground-penetrating radar and will analyze the atmosphere and surface composition using spectrometers. Together, these missions will provide a comprehensive picture of Venus, advancing our understanding by orders of magnitude. Beyond these approved missions, scientists have proposed even more ambitious concepts. One idea is a long-lived surface station, powered by advanced electronics that can withstand high temperatures for extended periods. Such a station could monitor seismic activity, weather patterns, and volcanic eruptions over months or years. Another concept is a sample return mission, which would collect rocks or atmospheric samples and bring them back to Earth for detailed analysis in laboratories. This would be incredibly challenging because of Venus's harsh environment, but the scientific payoff would be enormous. There's also interest in aerial missions, as I mentioned earlier. NASA has studied concepts like the Venus Atmospheric Maneuverable Platform, or VAMP, a solar-powered aircraft that could fly through Venus's upper atmosphere for extended periods. Such a platform could study cloud chemistry, search for biosignatures, and monitor atmospheric dynamics from a perspective we've never had before. The European Space Agency has explored the idea of high-altitude balloons, similar to those used by the Soviet Vega missions in the 1980s, which successfully floated through Venus's atmosphere for several days. Some scientists have even proposed submarine concepts for exploring Venus's ancient ocean basins if we ever confirm they existed. These would be purely robotic, of course, searching for geological evidence of past water, such as sedimentary rocks, mineral deposits, or erosion patterns. It sounds like science fiction, but so did landing on Venus before the Venera missions proved it was possible. The point is that Venus continues to inspire innovation. Engineers and scientists are constantly developing new technologies, new mission concepts, and new approaches to studying this challenging world. Every obstacle, the heat, the pressure, the acid, becomes a problem to solve, a challenge to overcome. And with each advance, we get closer to unlocking Venus's secrets.